Insulin. Is the control of insulin secretion finally something we've arrived at that is all about carbohydrate? Or is even insulin secretion mostly just about cellular energy status? Find out in today's lesson.
Ketogenic diet has neurological benefits. Why do we have to eat such an enormous amount of food?
Complex science, clear explanations. Class is starting now.
Hi, I'm Dr. Chris Masterjohn of chrismasterjohnphd.com, and you're watching Masterclass with Master John. We are now in our 23rd in a series of lessons on the system of energy metabolism, and today we are layering in, for the first time, the effects of hormones. And to begin our discussion of insulin, we're going to talk about what controls insulin secretion. We still at this point have been talking about fat versus carbohydrate. We're not ready yet to layer in protein because of its complexity. So although protein affects insulin secretion, we're going to talk about it only to a limited extent today, and we're primarily going to focus on fat versus carbohydrate. Nevertheless, we're going to tackle what seems like an incredible conflict between what we know about the effects of nutrition and what happened at the cellular level. Because we know nutritionally that you get more insulin when you have more carbohydrate and less when you have less. And yet when we look at the mechanisms governing energy secretion in the pancreatic beta cell, it seems to be all about energy status. So let's carve out this problem and show it exists, and then let's try to explain it. Shown on the screen is the design of a study looking at the effects of different meal patterns on insulin and glucagon. Glucagon is a hormone that opposes the action of insulin. Although it's associated with the fasted state, you also get a lot of glucagon when you eat things that aren't carbohydrate, especially protein. One of the reasons for this is that insulin, in the case of protein, is taking amino acids into cells. And if you just had protein stimulating insulin for that purpose, it would lower your blood sugar. So you need to have the opposing effect of glucagon to allow certain functions of insulin and prevent other functions of insulin that are undesirable in that context. We'll talk about that in much more detail when we get to protein. But for now, let's just take a look at these meals. We have an oral glucose tolerance test, which is 100% glucose. We have a high-fat meal that's deriving from fat 72% of its calories and only 23% from carbohydrate. We have a high-protein meal that's deriving 64% of its energy from protein and 26% from carbohydrate. And we have a mixed meal, which is really the high-carbohydrate meal. It's the meal that's 60% carbs. So all of these are mixed, but there's more emphasis on fat versus protein versus carbohydrate. In this diagram, plasma insulin following the meal is shown on the left and plasma glucagon is shown on the right. You can see that the glucose is shown with the filled in circles, and the glucose produces the most insulin and it produces the least glucagon. In fact, what you see here is that glucose on its own not only raises insulin, but it suppresses glucagon. High insulin and low glucagon gives you the most activity of most of the processes downstream from insulin. In other words, a high insulin to glucagon ratio gets you the most insulin signaling. The mixed meal, which is really a high carbohydrate meal, is next in line for high insulin and next in line for lowest glucagon. You see that protein and fat both stimulated similar amounts of insulin. Again, this is in the context of a mixed meal where there is carbohydrate in the meal, but having the predominant source of calories be protein or fat led to considerable insulin, and considerable glucagon. For insulin, the rise was fairly similar between the high-fat meal and the high-protein meal, but the insulin peaked earlier for the protein meal and peaked later for the fat meal. And for glucagon, the glucagon was highest in the high-protein meal and was next highest in the high-fat meal. So carbohydrate gives you the highest insulin to glucagon ratio and the highest absolute insulin amount. That translates into the greatest insulin signaling. Contrast this with what we know about what governs the secretion of insulin by the pancreatic beta cell. Inside the pancreatic beta cell, the single most important governor of insulin secretion is a high ratio of ATP to ADP. That means that it's the cellular energy status that is the central governor of insulin secretion in the pancreatic beta cell. This diagram shows what happens in more detail. And this is, in the context of a field over insulin secretion in which there are many controversies and disagreements, this right here on the screen is the one least controversial thing that you will find as the consensus in any scientific paper about what triggers insulin secretion. When you have a low energy state, you have more ADP and less ATP. This doesn't literally mean that you have more ADP than ATP. It just means relative to higher energy conditions, ADP is predominating. And when you have low energy state mediated through the ADP to ATP ratio, this activates potassium channels in the cell membrane. Those channels allow potassium to leave the cell. Potassium is positively charged, so having those channels open means a net loss of positive charge from the inside of the cell and a net gain of positive charge outside the cell. This leads to a polarization of charge across the membrane. Outside the cell is more positive in general because of the potassium. Inside the cell is more negative. When you have a polarization of charge across the membrane, you have a voltage. You have voltage-sensitive calcium channels that are blocked when the membrane is polarized. They're blocked in response to the voltage across the membrane. When the calcium cannot enter the cell, the calcium concentration inside the cell is low. Calcium is very frequently used as an intracellular messenger. A low concentration of intracellular calcium ions keeps insulin from being secreted. Some of that insulin is stored in the middle of the cell where it's ready to be moved at a later time. Some of that insulin is right associated with the inside of the membrane, ready to go when first called. If the energy state of the beta cell increases, you get an abundance of ATP relative to ADP. This change in the ratio inhibits the potassium channels. The potassium now cannot get outside, and that depolarizes the membrane, meaning the polarity across the membrane of charge, the voltage across the membrane, now dissipates. Positive charges can't get out, so now you have an equilibration where you have closer to electric neutrality on each side of the membrane. Since the calcium channels are sensitive to the voltage, this loss of voltage or depolarization opens up those calcium channels. Calcium comes into the cell. The rise in intracellular calcium stimulates a cascade of events that lead to insulin being delivered to the cell membrane with the vesicles opening up and allowing insulin to travel outside of the cell. This idea of changes in membrane polarization triggering some other event or cascade of events is extremely common in cellular biology. This is just one example of a common phenomenon. So, this being the part of insulin secretion that is not controversial means that what we know best about insulin secretion is that it's governed by the amount of ATP in the pancreatic beta cell. How can it be that nutritionally there's a specific effect of glucose, and yet at the level of molecular biology and biochemistry, it's all about cellular energy status. It's all about ATP. I believe the answer is that we cannot explain the specific role of glucose in insulin signaling by invoking biochemistry or molecular biology. I believe instead we need to invoke anatomy and physiology. Anatomy is the relationship between the organs and the other structural features of our body. Physiology is how metabolism is coordinated between those different organs to orchestrate some overall net result in the body that's more than the sum of its parts. So let's take a look at the anatomy and physiology of how carbohydrates and fats would reach a pancreatic beta cell. The pancreas is closely associated with the organs of the digestive system. Inside your torso, underneath the cavity where your lungs are, you have the liver, you have the gallbladder located tucked into the liver, you have ducts that lead together into the small intestine, you have the stomach, and you have that lead into the small intestine, the first section of which is the duodenum. The pancreas is tucked underneath the stomach, relatively close to the liver and gallbladder, but tucked into the curve of the duodenum, giving it very close access to the small intestine. It's important to realize that glucose or fat, when we first eat it, is going to go from the stomach into the small intestine. That does not mean at all that they have direct access to the pancreas. The reason the pancreas is tucked in with the duodenum is because it plays a role in digestion. Its role in responding to nutrients to secrete insulin is not related to the direct proximity to the duodenum. The key role of the pancreas in the digestive system is to make digestive enzymes. So we have bile acids that are made in the liver and come through the hepatic duct, can be stored in the gallbladder and come through the cystic duct into the common bile duct. And then the pancreatic duct takes digestive secretions from the pancreas, mixes them with the bile acids, and they get carried into the duodenum so that they can begin the digestive processes. If we look inside a pancreas, what we will find is 1 to 2 million islets. An islet is a collection of many cells involved in hormone secretion, which constitute the endocrine function of the pancreas. The islets are surrounded by circular arrangements of acinar cells in acini that are responsible for digestive secretions. These arrange circularly around the islet, and each of the acini is itself a circle of cells that can input the digestive secretions into the middle of those cells to be carried through the pancreatic duct into the duodenum. Inside the islet, we have many, many cells. We have alpha cells, beta cells, delta cells, and F cells. The alpha cells make glucagon, the beta cells make insulin, the delta cells make somatostatin, and the F cells make pancreatic polypeptide. Somatostatin and pancreatic polypeptide play special regulatory roles that are not of concern to us in this discussion. We're briefly touching on glucagon here, but we're primarily going to focus on it once we get to protein. For our purposes, what we care most about is that 70% of the cells in the islet are beta cells. How would carbohydrate and fat reach the pancreatic beta cell? Well, in fact, their transport is completely different. If you have carbohydrate coming into the small intestine, it's going to travel through the portal vein directly to the liver. It's going to go to the liver with all the other water-soluble nutrients in the diet. That means the liver gets first access to the carbohydrate. Well, that's important because the first thing you want to do with carbohydrate is replete your hepatic glycogen supply, because hepatic glycogen is what keeps your blood sugar stable between meals. So you can imagine already that if you're running low on carbohydrate, that in itself is going to make less carbohydrate ever reach the pancreas because it's going to go to the liver first to replete the glycogen stores there. The hepatic veins then take remaining carbohydrate into the inferior vena cava, which is the vein that's going to take those nutrients into the heart. From the heart, those nutrients reach the aorta, and they can go through multiple arteries to either circulate to many other organs or to go specifically to the pancreas. By contrast, if fats are in the small intestine, they're going to get packaged into lipoproteins, which are spherical particles that help them transport through our system and are called chylomicrons. The chylomicrons are going to leave the small intestine through the thoracic duct, which is part of the lymphatic system. These chylomicrons are going to have long-chain fats and any other fat-soluble nutrients. These fats are going to go through the thoracic duct as part of the chylomicrons and then empty into the inferior vena cava, which is where they first reach the circulatory system and which is the part where they share in common with the travel of carbohydrate that had come from the liver. Like the carbohydrate that came from the liver, the fat that came from the lymphatic system that never yet went into the liver is going to reach the heart first. It's going to go through the aorta. From the aorta, it goes through multiple arteries that can take it to the pancreas or to the many other organs. So the two key differences between carbohydrate and fat so far is that carbohydrate goes through the portal vein and the liver has first access before it ever gets to the heart or pancreas. Fat goes from the small intestine through the lymphatic system, never goes to the liver until after it goes through the heart, which has first access, and then to the general circulation where it can reach the liver or the pancreas. If we look at how the fat or carbohydrate would get inside cells, it gets even more different. We digest carbohydrate to free sugars. In the case of starch, for example, we digest it into glucose, or if we eat glucose, we get free glucose. If we have free glucose, it transports right into the cell through the glucose transporters in the cell membrane. This is a very simple transport system. The transport of of fats contained in chylomicrons is quite different. In certain cells that make the enzyme lipoprotein lipase, they can send the enzyme out into the capillary beds that nourish them. So let's say this is the heart. The heart cell makes LPL, puts it out into the capillaries nourishing the heart. Same thing with the muscle. The muscle cell makes the LPL, sends it out into the capillary bed. The capillary bed is made of capillaries, and the lumen of the capillary is the area in which blood flows. That lumen is enclosed by the capillary endothelial cells, which make the lining of the capillary. The lipoprotein lipase, or LPL, will come out of the cell that made it and become embedded in the capillary endothelial cell. That LPL will then take chylomicrons and digest their fats into glycerol and fatty acids. The chylomicron gets digested into a chylomicron remnant, and that chylomicron remnant is later taken up by the liver. Meanwhile, the glycerol and fatty acids are available to the tissue that made the LPL because the job of this capillary is to feed that tissue. So those nutrients get digested in the capillary and infuse into the cell. The expression of glucose transporters and LPL is very different. If you look at glucose transporters, all tissues in the entire body express GLUT1 and GLUT3. These glucose transporters are high affinity for glucose and not dependent on insulin. That gives all tissues access to the glucose that they need under any condition. The liver and pancreatic beta cells also make GLUT2. GLUT2 has low affinity, meaning it's only activated at high concentrations of glucose, and it's not dependent on insulin. That allows the liver and the pancreas to ramp up glucose uptake when blood glucose concentrations rise beyond their normal level. In addition, muscle, heart, and adipose tissue make GLUT4. GLUT4 has moderate affinity, and it's increased by insulin and AMPK. AMPK increases GLUT4 because the cell needs more energy. Insulin increases GLUT4 because the body needs the cell to take up energy or to take up specifically glucose. So we have all tissues expressing GLUTs, some more than others, some extra GLUTs that play specific functions, such as response to insulin, response to energy status, or response to circulating glucose. If you look at the expression of LPL, it's expressed much more limitedly. Almost all of the LPL is expressed in muscle, heart, and adipose tissue. We know most about the LPL that's expressed in those tissues. What we know is that high energy status shifts expression away from muscle and heart and toward adipose. By contrast, low energy status does the opposite. So think of the fat traveling through the meal. Remember, it goes to the heart first. If it goes to the heart first, then if energy status is low and the heart really needs fat, the heart gets first access to that fat and takes it up. But if energy status is high, the heart just looks at the fat and is like, nah, I don't want this. That leaves more available to muscle and adipose tissue. But muscle also looks at that fat and says, I don't want this. By contrast, adipose LPL is high under conditions of high energy status. That makes fat go to adipose tissue under conditions of high energy status. Meanwhile, there is also LPL expression in macrophages, lung, kidney, brain, and lactating mammary gland. The expression is much smaller than in muscle, heart, and adipose tissue. The regulatory mechanisms are diverse and poorly understood. A typical review of LPL expression across tissues won't even mention its expression in the pancreas. But if the pancreas doesn't make LPL, how is it supposed to take up postprandial fat from chylomicrons? If you know studies that look at human beta cell LPL, please send them to me. I couldn't find any, but I found studies in mice. And what these studies show is that in mice, pancreatic beta cells do make LPL. However, under almost any condition, the LPL is inside the beta cell. If the LPL is inside the beta cell, that means there's no LPL in the capillary lumen. That means there's no LPL to digest chylomicrons. That means that LPL does nothing to get fat into that beta cell. They've taken the mice and they've subjected them to fasting, to refeeding, to a normal chow diet, to a high-fat diet, and the LPL just sits in the pancreatic beta cell. The only conditions that make it leave the beta cell and go into the capillary lumen in these mouse and mouse cell experiments is high glucose concentrations. We're talking 20 millimolar, conditions of untreated diabetic concentrations of high glucose. That means that only under conditions of very high glucose would you ever get fat going into the pancreatic beta cell through locally expressed LPL. But there's another way that fat in the postprandial state could reach the pancreatic beta cell, and that's from fatty acid spillover. Let's say you have an LPL-producing tissue that puts LPL into the local capillary bed. It digests chylomicron triglycerides into free fatty acids and glycerol. In general, these are completely or mostly taken up by the LPL-expressing tissue. But what if you have so much fat that you overwhelm that tissue and there's no room to take up all the fat that's been digested? Or what if you're fat? What if that tissue is fat and all the room within that cell is taken up by fat? Or what if the energy status of that cell is so high that it's blocking the uptake of everything? In those cases, you may get digestion of the chylomicrons into free fatty acids and glycerol that get left in the blood. And since they don't get taken up by the tissue, they leave the capillaries through the veins, and then they eventually make their way into the circulation to get to other tissues such as the pancreas. That's called fatty acid spillover, and it's thought to be increased by high-fat diets, obesity, and insulin resistance. So far we have glucose going to the liver first and repleting the hepatic glycogen. Whatever glucose is left over goes to the heart and eventually can make its way to the pancreas. By contrast, fat goes through the lymphatic system, goes first to the heart. And if the energy status in the heart is low, the heart gets first dibs on the fat. If it's high, that fat preferentially goes to adipose tissue, not necessarily ever making it to the pancreas. Glucose transporters are expressed in the pancreas. In fact, the pancreas also expresses GLUT2, a special glucose transporter that makes glucose uptake kick in even higher than normal whenever circulating concentrations of glucose are high. The liver does the same thing. That means that high blood glucose goes preferentially first to the liver to replete hepatic glycogen and second to the pancreas for insulin stimulation. In addition, the pancreas also has a special form of hexokinase that doesn't get inhibited by glucose 6-phosphate. We talked before about how if you don't go through glycolysis, glucose 6-phosphate builds up and that rejects the glucose. In the pancreatic beta cell, we have glucokinase, a special form of hexokinase that is not inhibited by glucose 6-phosphate. That means that the pancreatic expression of glucose transporters and hexokinase isoforms is designed to facilitate glucose uptake into the pancreas, not because the pancreas needs more glucose, but specifically because the circulating glucose concentrations are high. This is not true for fat because the pancreatic beta cell appears not to move LPL into its local capillary bed unless possibly exposed to very high concentrations of glucose mimicking untreated diabetes. But the pancreatic beta cell still gets some fatty acids in the postprandial state from fatty acid spillover if the meal is very high in fat or if the person is obese or insulin resistant. So it seems then that it is the anatomy and the physiology that coordinate the inter-organ distribution of these nutrients that drives the effect on insulin secretion instead of the biochemistry and the molecular and cellular biology that occurs within the pancreatic beta cell. Nevertheless, the mechanism that I showed you at the very beginning is what's called triggering. There's also an amplification step to insulin secretion, and the amplification step is much more complex and much more controversial. So let's say that it's glucose that is primarily the nutrient that can raise ATP levels in the pancreas, inhibiting the potassium channels, depolarizing the membrane, activating the calcium channels, getting a rise of intracellular calcium, initiating a cascade of events that leads insulin to be secreted. Well, there's that, and that's the uncontroversial consensus part of this. But the amplification step can make the cell more sensitive to the influx of calcium, or can increase the capacity to respond to that calcium by making more insulin ready to be mobilized. And these amplification signals are, number one, very complex, and number two, not at all agreed upon. We may be moving toward a consensus eventually, but if you look at even recent reviews of this topic, you'll see lots of controversy about which mechanisms are more important, and even some controversy over which mechanisms actually play out in the live human at all. If we look at these amplification signals, what we will see is that anaplerosis, which is the filling up of citric acid cycle intermediates, can occur in a way that overfills the citric acid cycle and leads to cataplerosis, which is the leaving of citric acid cycle metabolites, including their transport into the cytosol. Since anaplerosis is primarily the domain of carbohydrate and as a secondary source protein rather than fat, then that means that cataplerosis is primarily enabled by carbohydrate and secondarily protein. That cataplerosis then leads to amplification signals. Lipogenesis leads to various downstream processes from the accumulation of fat in the cell. Lipogenesis is driven by malonyl-CoA. Malonyl-CoA can be derived from anything that makes acetyl-CoA and citrate, because citrate activates the conversion of acetyl-CoA to malonyl-CoA, as we talked about in the lesson on fat burning. Since carbs, protein, and fat can all generate acetyl-CoA and can all generate citrate, then carbs, protein, and fat can all lead to malonyl-CoA and lipogenesis, and can all, to some extent, lead to that amplification symbol, that amplification signal. Some of this is driven by the pentose phosphate pathway's production of NADPH, a topic that we haven't covered yet. It's carbs specifically that support the pentose phosphate pathway and provide that NADPH that go into that amplification signal. So what we see then is that all of the macronutrients can make some contribution to amplification, but carbohydrates are the most versatile out of all of them, and fats are the least versatile. Perhaps that versatility in providing the amplification signal is simply a way to gauge the versatility of carbohydrate, because carbohydrate is also the most versatile in supporting the biochemical pathways that you actually need. So if the body is trying to judge whether it has enough energy, it makes sense that part of that signal would be specifically driven by carbohydrate, because carbohydrate is the thing that supports the pentose phosphate pathway, whereas fat doesn't. Carbohydrate is the thing that supports anaplerosis of the citric acid cycle, which fat doesn't, to anywhere near the same extent. And so it may actually be that the pancreatic beta cell is, as the mechanism of triggering would suggest, simply gauging energy status. And it may be that the pancreas correctly looks at carbohydrate as a specially valuable source of energy, because the energetic uses of carbohydrate are more versatile than those of other macronutrients, especially fat. And if carbs provide energy plus the specific uses of energy that fat can't, then carbs are a uniquely valuable source of energy. So when I look at this, what I see is the pancreatic beta cell wants to make sure that we have enough energy. But it wants to specifically make sure that we have enough glucose because of the specific things we can do with that energy that are much harder to do with the energy we derive from fat. So is insulin responding to carbohydrate specifically, or is it responding to energy status in general? The answer is both. The anatomy and physiology bias carbohydrate to the pancreas when it reaches high concentration, providing the liver has had the first opportunity to replete the hepatic glycogen pool. That same anatomy and physiology biases fat toward the heart and muscle under low energy conditions and toward adipose tissue under high energy conditions, and biases it away from the pancreas under any conditions except possibly severe hyperglycemia. Then, the biochemical pathways within the pancreatic beta cell are mostly responding to cellular energy status. But because the pancreatic beta cell's energy status is best nourished by carbohydrate, then carbohydrate plays a specific role in triggering insulin. Carbohydrate also plays the dominant role, with protein second and fat a distant third, in amplifying that insulin signal, because, perhaps, the pancreas cares that we don't just have enough total energy, but that we have the versatility that we get from having carbohydrate as a part of that energy. The audio of this lesson was generously enhanced and post-processed by Bob Devodian of Torian Mixing, giving you strong sound and dependable quality. You can find more of his work at torianonlinemixing.com. To continue watching these lessons, you can find them on my YouTube channel at youtube.com/ChrisMasterjohn, or on my Facebook page at facebook.com/ChrisMasterjohn, or you can sign up for MWM Pro to get early access to content, enhanced keyword searching, self-pacing tools, downloadable audio and transcripts, and a rich array of hyperlinked further reading suggestions, and a community with a forum for each lesson. If you really want to own these lessons, study them, and get the most out of them, sign up for MWM Pro at chrismasterjohnphd.com/pro. Signing off, this is Chris Masterjohn of chrismasterjohnphd.com. You've been watching Masterclass with Master John, and I will see you in the next lesson.